Hello, everyone, and welcome back to NLP for All, where we talk about natural language processing and some useful tools and techniques for processing text-based information. Uh, Today's session, we will be looking at speech technology and all of the ways in which natural language processing interfaces with speech data. For today's session, the notebook that I'll be using is in the table in our NLP for All repository. I will share the link in chat. Now, if you click on the link to notebook, it should open up a page that leads you to a Python notebook with a button which allows you to open the notebook in Colab. And that should reveal the notebook that I will be using today. Let me make my font size a little bigger. Okay. So when it comes to speech technology and automatic speech recognition, what we're essentially talking about is a method in which a speech signal can be taken as input, a mathematical representation created for the speech signal, and then a transformation or a series of transformations that turns this speech signal into meaningful text. For this process, we would need acoustic models to actually process the speech. We would also need lexical and language models in order to convert and chunk our speech data and extract words, sentences, and characters. So broadly speaking, the process and pipelines both are part of speech technology. We record, encode, process, and decode spoken language. And our purpose for doing this is for downstream tasks. Some of them could be just speech-specific tasks such as voice recognition and denoising. Others could be more language-based tasks such as transcription and machine translation. Now, when we combine speech processing with NLP, we're looking at human language at multiple linguistic levels. So the first one would be the raw acoustic and phonetic phonological level. And then we're also looking at the lexical, morphological, syntactic, and cognitive levels. So we're looking at language both in terms of its output as well as its representation in a language system. When it comes to recent advancements in deep learning with our hardware advancements in GPU technology, speech technology has become more usable. We're able to transform text in real time. We're able to translate text in real time. And we're also able to synthesize accessible and natural sounding human-like voices. Why would we use speech processing and speech technology? Some of the popular use cases for using for speech technology include speaker diarization and biometrics. So if you have a sound file that has 5 people talking, is there a way in which you can separate the audio channels for each of the 5 speakers? And if you can do so, is there a way in which you can use a person's unique voice signature in order to identify them? Right. The next, another popular use case is captioning and transcription. So if you are joining me on Zoom, you'll notice that we are generating automatic transcripts for this session, and that's happening with a speech-to-text system that Zoom runs. We also use speech technology for voice typing, which many of you might have observed on your laptop computers and your smartphones. Then another popular use case is sound source identification. So if we have a convoluted signal and we want to find out what are the different contributors to the signal, speech technology can help us identify background noise. It can help us identify different bird calls in a video, in an audio. It can also help us identify a song if we have a piece of recording. And it also helps us identify number of languages that are present in a speech recording. right? Speech technology is also useful for creating voice assistants and voice activated technology. It's also good for emotion, sentiment, and voice recognition, which because a lot of our speech mannerisms tell us how someone is saying something. So are they sounding angry? Are they being sarcastic? What is their speaker intent? Or when we utilize a speech signal along with NLP tools, we get better results for tasks such as emotion and sentiment detection. Other examples include machine translation and language detection. So if we do have a speech signal, there is technology available that can tell us what language is being spoken in the background, which can be really useful for streamlining our transcription task and making things faster. Now, at this point, I'd like you to think about the different voice technologies that you may have encountered this week. Next, I'll move to a brief look at the pipeline that an ASR and a text-to-speech system uses. So if you look at this image, we have a input that is the question, what is the weather like tomorrow in London? Now, this happens to be an audio input. The first thing that happens is we want to make sure that the input that we're providing is machine readable somehow. So this includes the steps of feature extraction, and then once the features have been extracted, they pass through an acoustic model, and we're trying to create a representation for our system. Next, we want to make sure that the acoustic output from the first part of our pipeline is transformed into text so that we can understand the words that were present in the recording. Right. And once we have the text extracted from a speech signal, we can conduct a natural language understanding task. So this could include actually searching for the information that our user requested, finding a way to understand what they said, maybe translating it into a language that they might want. And once the natural language understanding component is done, and we have an answer to the query that our user asked, the next thing that we want to do is convert it back to speech so that our voice assistant can respond to the user. And so in this case, the text to speech component of our pipeline takes over, where we convert the text back into a natural sounding voice and provide our user with an answer to the query and provide them with a voice recording that is responding to them. So when we discuss speech technology and speech processing, it's important to keep some basic terminology in mind. A lot of this terminology, you'll encounter this in papers and readings that you come across on the topic. The first, and some of them are words and topics that I just addressed in my introduction. So the first example terminology for us would be automatic speech recognition. Broadly speaking, this is a conversion of spoken language into text. It involves recognizing speech patterns and then turning them into written language. Next, of course, we have NLP, which I have discussed considerably in this series. Then we have speech synthesis, where we have an artificial production of a human-sounding voice that's being done with the help of speech models, language models, and algorithms. When we talk about text-to-speech specifically, it takes text prompts as its input and provides a voice recording as the output. A voice user interface is the space which allows it's a application that will allow our users to use their own voice recordings in order to provide the input instead of text. The modeling that happens for our voice data utilizes acoustic models, which are probabilistic or deep learning models that are trained to represent a relationship between the different linguistic units, so the different phones, and the audio signal that is being associated with them. And so essentially an acoustic model helps us break or chunk our audio signal into smaller units of sound. Associated with our acoustic model is the language model, which is actually going to help us take these little chunks of sound that we just processed, do some kind of pattern recognition, and tell us what kind of words are these sounds forming for us. Another useful term is the wake word definition. If you've used voice-activated technology, many of them require a word to start the application up, and that is termed as the wake word. So when it comes to the history of speech technology, or how did we get here, there's been a considerable amount of work on speech processing all the way back from 1784 to today. We've been most scientists who work with speech signals have been working very hard over the years to find a way to build a machine that can talk back and understand human speech. So we started with acoustical mechanical models, and very quickly in the 80s all the way until the 2000s, we moved to more probabilistic models. Many of these were for security, privacy, and intelligence, developed for intelligence purposes. And the major breakthroughs happened in the last 15 years when speech recognition made its way from very big and bulky systems all the way to smaller smartphones with voice assistants. Now, before I move to the specifics of speech technology, I did want to provide a little background on what it is that speech technology deals with when it comes to linguistic representation of sound. I consider this the shortest primer on two major subdisciplines in linguistics that I can possibly provide. The first thing to keep in mind is, because we are talking about speech signals, it involves sound propagation. Speech is a sound wave. It's a longitudinal wave. It involves compressions and rarefactions. Sound can only move through a medium, and so on Earth, this medium happens to be air. And when it comes to specific concepts, some of the things that we keep in mind when we're looking at our speech signal is things like amplitude, so how much energy is in the signal. It's also important for us to know the frequency and time information. When it comes to a human voice, this is a complex wave that has multiple frequency components that get encoded together. In order to represent this sound wave, we use spectrograms, and waveforms, which are just different ways of plotting the information to make sure we can distinguish between two different sounds. Once we have our analog signal, in order to digitize the signal and actually provide it as input to machines, we conduct things, we use algorithms like the Fourier transform and the fast Fourier transform, which gives us the information that, which gives us a representation of a wave in the frequency domain. So it tells us, it gives us specifics of the kinds of signals that are encoded in a sound file. When it comes to distinguishing between different vowels, for example, we might use ferments, which are just different, which give us information about tongue position and oral cavity shapes, which in turn tell us what kind of vowel was produced by simply looking at the speech signal, which is very similar to how our ear processes spoken speech. And then some of the other acoustic features that get extracted when we run an acoustic model are things like MFCCs, which again are a representation of sound in a power spectrum way. It just gives us another representation of a sound signal. And because it's very close to how the human auditory processing works, it's a great way, it's a great numerical or like mathematical representation of sound that a machine can read and process. So at this point, maybe I'd like to move to simply creating some sound waves. So in this case, as an example, I'm creating a sound wave which has a particular frequency. So you'll notice that in this example, I'm using this code to generate a tone, in which the frequency is 5,000 hertz. So if you run this code, you'll get a little sound box, and if you play it, it'll give you a monotone, not the world's cleanest tone, but just an example. And if you if you want to see what this sound wave actually looks like, I have some visualization code over here. So if you look at the plots that this generated, you'll notice that it's a wave that is vibrating at a particular frequency. So the little peaks and troughs are very predictable and go at a particular way. If I wanted to look at this sound in the frequency domain, if I wanted to get some information on how often are these vibrations happening, at this point, in the frequency domain, it gives me exactly one line, which is at 1,000. The magnitude is 1,000, and if we look at the frequency information, it's right there. And we also have a spectrogram, which is just telling me if I was to play the sound for, say, a certain number of 1.6 seconds to be exact, what does the sound look like? Okay. We can also generate a few other sounds over here, in which, if you run the next couple of codes, this generates a vowel sound versus a noise sound. Now, this is a very important distinction because essentially any kind of tool that wants to separate out noise from sound that has information encoded in a particular way, the distinction would be between vowels and noise. And so if you were to play the audio files that are generated, vowel sound and noise sound, you'll notice that there are some very key differences that your ear can pick up between them. So if you play both of them, and you'll notice that the noise, the vowel sound tends to be a flat, straight tone. When it comes to the noise sound, it almost sounds like someone is blowing air into a microphone. And so this distinction between noise and signal is going to be very important for any further discussion of speech technology. Now, once we have the basics, the physics, as it were, of our speech signal, the next question for us is, how do we take this raw signal, which is just a bunch of mathematical numbers, just information about amplitude and frequency and time, and how do we actually go from that to actual sounds that we can distinguish between? So this is where the domain of phonology and phonemic inventory come in. When it comes to specific terms, some of the things that we're doing, we are trying to extract phones from a given signal. So we want to make sure that when our speech signal is being processed, we are extracting the smallest unit of sounds, and each sound should be different from none other. So if I have the two words pit and pat, there is a difference in meaning between these two words. And in terms of sound, the difference is the vowel that is in both of these sounds. So any system that needs to process these words will need a method that can make sure that the three sounds in each of these two words can be separated out, so that we can specifically say that the vowel in both of these words, pit and pat, are different. So broadly speaking, that's something that is very important for us to process our speech signal. And there is a little bit more information on how this happens and why it happens, and how it relates to all of the other linguistic levels, like processing text and extracting words and sentences from a sound. And most of that I have discussed over here. I know that some of it might be very heavy in terms of detail, but I will leave you to peruse it if you're interested. The broad tax of why we discuss this would be, if we want a speech signal or a sound file to actually be useful for us in a NLP task, we have to make sure that the sounds inside this file can be easily differentiated. If these sounds can be easily differentiated, then they can get easily combined to make words, and our system can combine them in a probabilistic manner to tell us what kind of words are in the signal, right? And another important key thing is that whenever we produce sound, whenever we use our vocal cords, we are using them in a purpose-driven way for the most part, unless you're a baby and you're screaming. And so because our sound production, our speech and sound production tend to be purpose driven, it's very straightforward for us to take a speech signal and extract meaning and language from it using NLP. Right. Now, if you're interested in looking at how the articulatory system works, the pink trombone demo is a great example. I will briefly play it and show you what it looks like. So it's just a website with a shape of the human oral cavity, and you can use this example to create different shapes and see how sound changes when you make changes to the different oral cavity shapes. And what our ear is doing is it's picking up these differences in shape, and it's trying to understand what words we formed, right? There's also an acoustics demo, which is just the interactive ear demo. And in this example, we just have it's just a great look at what the human ear is, how it works. You can click on different parts of the screen to learn more about how the ear works. And another useful tool if you're interested in how the human perception system works, right? Now, there are a few other things that terms that you might encounter when you study speech technology. Some of this is the difference between analog and digital signals, the actual processing of an analog signal in order to make it machine readable. And there are some other key terms that are worth keeping in mind when we talk about digital signals. But I'll leave you to get a better sense of it if it's something that your work needs. Um, in terms of in terms of our hardware and in terms of our data, just one important thing to keep in mind when it comes to any kind of sound processing. Many of our sound files are stored in all kinds of formats. So I'm sure you're familiar with the MP3 and M4A and MP4. Some of the other formats include FLAC and WAV. The main thing when it comes to these different formats is that there are free tools available to convert from one to the other. So when you are using a specific ASR model, or if you're using a specific tool, you might need your audio to be in a specific format. And like there are some options on such as the FFmpeg tool, which you can use through your command line. And these will allow you to convert from one format to another, and you can use any audio in any of your pipelines. So this part can be a little daunting. So if you do come across a cool audio processing tool and you're struggling with getting it in the right format that the system wants, there are free tools that are available, and it's very easy to make sure that your audio files are always readable and usable when it comes to the system. Now, I'll take a brief pause here and allow you to go over the systems and terminology and definitions that I used. And please let me know if you have any questions. The next part will focus on some speech technology demos, and I'll get started in a minute. Okay, so having talked about the theoretical aspects of speech technology and phonetics, it's time to move on to some demos and some actual use cases where speech technology is useful. The first example that I wanted to touch on is a text to speech or speech synthesis. Specifically, when we talk about text to speech, it involves providing our system with a text input. So we provide it with a sentence that's been typed out or an entire document. And then our expected outcome is a sound file. So this could be a sound file in a waveform or MP3 form, but essentially a sound file in which we have a synthetic voice that is reading out or speaking the text that we provided it. Um, and for this example, I'll be using a free text-to-speech processing tool known as Koki. Koki has a lot of pre-trained models in multiple languages, and it's a really useful tool for text-to-speech. It's free and it's pretty lightweight, and so you'll be able to run it on Google Colab. It's also possible to run it on CPU, although it might be slow. So you can even install this on your local system and give it a go and see how it works. The code for running it on CPU will be a little bit different, but it's the Koki website has many demonstrations to help you achieve this. And Koki also has a really lovely community, so you can always reach out for help and get support. Right. At this point, I will be simply going over the code output. I have been, as always, rate limited by Google Colab. And so I have managed to run all the code, but if I try to run it again, I might run into trouble. So I'm just going to go over the output. I encourage you to run the code blocks in this section and see if you're getting the same expected output as me. So we start with our installation. So we need a text-to-speech system, and we need, because I'm using the TPU, the Google Colab GPU today, I'm going to also need Torch. So at this point, please make sure that in the top corner, the selected runtime is a T4. You can, in case it says CPU, you can change the runtime type by clicking on Change Runtime Type. And then I'll move on to installations. In case you run into bugs, I've also upgraded the NumPy and Pandas libraries just to make sure that there are no version incompatibilities. The main code, of course, is our importing the models and then using the interface to run our system. So over here, we'll be importing the TTS library, which is going to help us actually conduct the text-to-speech. And it's also going to help us list all of the available models. So if your code runs correctly, you should see an object getting printed. And if you run the next code block here, I'm asking it to print all the available models that got downloaded or are available to me if I'm using the Koki TTS system. And if you're able to run this, you'll notice that there's a whole bunch of names. It starts all the way from our 4 multilingual data sets. And then we have the different language codes. So EN over here is English. So you'll see that there's a lot of pre-trained models available for English, but then there's also different models for German, Italian, Brazilian Portuguese, Spanish, and so on and so forth. And there's a full list that you can also look at. Now, the list of models has been, you'll notice that it's been broken down. This is also because Koki allows users to implement and input other pre-trained models that are available. So this is a very exhaustive list. For today's example, we're going to use a multilingual model. And this multilingual model has a few language options, and I'm going to test 2 of them. The first thing that we want to do is we want to load our multilingual model. And so I'm using from my list, I picked out the multilingual model with the name that's present over here. If your model installs correctly, you'll see some model details getting printed. And then we're going to simply get a sound file from one of our, from the Gen AI workshop that happens at 1 p.m. If you're interested, please do stay back. So I have a simple voice file that I'm going to use today. So in this example, I'm going to use the English sentence, "This is voice cloning," and I'm asking my model to save the sound file to the file called output.wave. So if you're able to correctly run this system, it will generate a small sound player for you. And if you click on it,
this is voice cloning.
The file will read out the words that we gave it. And if you'd like to test this code with something different, please feel free to substitute "this is voice cloning" full stop with a different piece of text, see how it works. I have given only 4 words over here. See how the system does if you give it 12 words or 13 words. Like in this example, I've also provided it with a speaker voice that I want. There are some other options for you as well. So this is the first example where I'm giving it text in English. And the way the code is set up, it gives me a little voice player. And you will notice that output.wave also gets saved to the Colab file list. The next thing, because there are a few other voice examples, I'm going to try, I believe this is Brazilian Portuguese. And so there's a sentence here, again, a couple of words. I've used a voice and I've asked for a voice output. And so if this code has run correctly for you, you'll see another voice player over here.
Isso é clonagem de voz.
And if you click on it, it'll read out the words that were printed here. Right. So the first basic use case for any kind of automatic speech processing would be generating speech. And these are 2 examples of how to do text-to-speech. Now, the next example for us, the next use case for us.
Can I ask a question over here?
Yeah, sure.
Can I go back to the code where you generate this is the voice clone? So does it mean that for every time I have to download the sample voice first, are there any like library where I can get the voice directly?
That's a really good question. There are a few options for that. You can also record a voice sample if you want.
Okay.
So basically, it's just a if you follow this link along, you'll see that it's just a voice. It's just an audio file. And so if you can generate a similar audio file, then that's just the voice that you can use. So it'll ask you to download. So if you click on allow and you play the file, you'll see that it's just a basic sound file. And we just want to make sure that that there's some basis or some kind of a system that we can use. So let me just play this for you real quick.
Hello, this is my voice. I'm going to use this voice to guide.
I don't know, is the voice output, does it work?
Yeah, it works. So
okay.
The input doesn't have to be long, right? I can use any length for the input.
Yes, you can use any length. It's just if you make it too long, then the processing takes too long. And if it's too short, then all of the sounds, basically all the phones are not represented well. And so the quality of your output may not be great.
Okay, thank you.
Right? Yeah, so and then because this is an example of voice cloning, we're providing it with a sample voice. But if you're interested in voice cloning for I don't know, George Clooney or some celebrity, a similar, you could find a sample audio of them speaking and see if the model is able to recreate their voice.
Thank you.
Okay, yeah. Thank you for your question. Okay, so in this example, the sample voice is speaking in English. And when we change the language, we find that because the model that I selected is multilingual, it's able to use the same voice and get it to speak Brazilian Portuguese. So again, the sample audio is essentially giving us some voice characteristics of a person. And it's the text-to-speech system that's doing most of the heavy work. Okay. Now, after voice cloning and text to speech, the next major use case would be noise reduction. So if you have encountered recordings, if it's a podcast or a movie recording or some high quality setting, you'll notice that the noise levels, the environmental noise, the clangs and the clatter and sounds of I don't know, birds or traffic or any other things happening in the background are kept quite minimal. If you've listened to Zoom audio, you'll notice that Zoom also automatically suppresses a lot of background noise. It's not very great at, I don't know, dog voices and baby voices, but it does a pretty good job for all kinds of other sounds that make our signal a little more difficult to listen to. So for noise reduction, we'll be using a tool called Speech Brain, which is just a system with, it has a whole bunch of pre-trained models that are specific for different use cases. And many of these tools allow us to improve the quality of our system. And essentially, many of these tools do is they have a great model that is able to identify speech. Because it's able to identify speech, it's able to distinguish between speech and non-speech. And so it's easily able to filter out things that it considers non-speech. Okay. So for using Speech Brain, we'll be downloading and installing the system from the Speech Brain's GitHub repository. It is freely available. And I'll be using a few other tools as well, just for this demonstration. Now, most of these examples are from the Speech Brain from their own demo, and they have a fantastic documentation system, and so most of it I'll be using directly. Now, in this case, they've provided a few example audio files in a Dropbox folder. And so if you see any wget commands, I'm essentially downloading those files so that I can use it for this example. So the first model is a separator. So what does it do? It's going to take a sound file and it's going to perform certain transformations on it. So I have two examples over here. One is the raw signal, and the second one is the signal with certain enhancements. So if you take a minute to listen to both of these audio files.
It is very much music. That is why I buy bonds.
Now you'll notice that in the first example, the audio was recorded in a very in a noisy space. So there's a lot of background noise. And if you play the enhanced speech, the audio file in which the processing
and that is why I buy bonds.
Sorry, let me play that again.
It is a very risky business, and that is why I buy bonds, period.
So if you notice, the background noise got filtered out, and the only thing that got preserved by the algorithm is the speech. The next use case for us is if we have multiple speakers, is there a way to separate them out and preserve each of the voices separately? So for this example, again, there's a mixture audio file that I'm downloading using wget that should basically save a WAV file to the Google Colab files. And so if I'll play each of these sounds.
My father has revealed the culprit's name.
So in the first example, it's a convoluted signal. There are actually two signals that have been mixed together. And so when we run the source, when we ask Speech Brain to separate out the sound file by source, we get two audio files because one for each of the audio that got mixed in the original audio. And so if I play each of them.
My father has revealed the culprit's name. The birch new slid on the.
Right. So these are completely different sentences. And so when we try to when we run the est_source command, what it's doing is it's separating out these sounds for us. Again, this is a different model that's been specifically trained for this purpose. The third example that I want to look at today is speech verification. What speech verification does is if you provided two audios, audio 1 and audio 2, it's going to try and see if the voice characteristics of audio 1 and audio 2 match. And this provides us with a score and a prediction. So it tells us how similar does it think the voices into audio files are, and then it gives us a true-false prediction, which tells us if a given speaker, if the speaker in both of these audio files is the same speaker or different speakers, right? So if you run the code, the first thing after it's done processing the example, you can play the two, I'll be playing the two examples here.
The birch canoe slid on the smooth planks. My father has revealed the culprit's name.
So this is the separated audio from the previous example. Just by listening to it casually, we can tell that the voice characteristics of both the female voices in these examples is not the same. And when you ask the speech brain voice verification algorithm to assess if these are the same or different voices, it gives us a prediction. The prediction is false, and it says that the score of the similarity score for both of these is 0.17. The higher the score, the more similar they are. The lower the score, the less similar they are. And in this example, in case you'd like to try this out with a voice recording of your own, you can go to the folder icon over here, and you can upload a couple of files. And as you can notice, as you may have seen, any format works. SpeechBrain is very good at processing audio files across different extensions. So all you have to do is upload a couple of files that you want to speaker verify for. You can simply change the file name in the examples, and if you run it, you can see how well the model does. Does it do better if you have two child voices, for example? Does it do better for male voices versus female voices? How does it do if the voices don't have a easily identifiable gender? All valid questions. And this is the point where I leave you to test this out and try and see how the model does. Right. So this brings me to the end of all the demos that I have for you today. There were a couple of other demos. If I'm able to go over them, I'll try and add them to this YouTube video. Some of the other references and sources that I used for compiling today's workshop are provided here. Something that, in case you're interested in demos and games, a very popular game among phoneticians is Grammel. It's a Wordle, but for speech signals. So every day we get a new speech signal. We get the waveform and the spectrogram, and we have to try and identify what the words are that have been spoken in the signal. So if you're interested in learning more about that, please let me know. I'd be happy to share more resources. And another thing is, yeah, if you've had any trouble with running the code, or if there have been any issues, please let me know. Thank you so much for attending, and I'll see you next week. Next week, I will be looking at a little bit going more into the specifics of speech technology, and what I will be looking at is converting speech to text. So how to conduct transcription using Whisper AI. Whisper has a lot of language options. It has a lot of transcription generation options, and I hope you can join me next week for learning how to run Whisper using your own local system or Colab. Thank you so much for being there.
Thank you. It's really informative. Can I have a question? Just maybe earlier, maybe it's more related to next week workshop. So I was thinking about doing like voice to text, but for the input, some of the input may be bilingual, such as like English, Spanish, which is like similar, but some could be like English and Chinese, where the sentence structure will be very different, but
Right.
like the speaker will speak both together. So
Right.
does the current library support those combined language, or is there a way to process it?
So based on my runs, like the experiments I've conducted, bilingual speech, it can be processed, especially if one of the languages is English. Whisper is a multilingual model, so it is the model is trained on multiple languages by default. And of course, Mandarin as well as Spanish are very much those languages. So if you're in a hurry, you can take a look at the notebook and try and run it. I have provided examples for Korean, but basically, as long as you know the language code, you can run it for English and Mandarin. Another thing, Whisper has, if you don't provide it with the language, it takes the first 30 to 40 seconds of the audio and it predicts what language is being spoken. And so it does a language identification and then it transcribes the entire audio based on the language it identified. So broadly, if it's a multilingual speech or bilingual speech and one of the languages is English, Whisper should be able to take care of it. You can tell Whisper to specifically look out for certain languages. And yeah, the model, if you want to assess how well your model performed, you could, there are tools like word error rate, which can tell you how many mistakes were made. And that's something that you can use to assess how Whisper did. And Whisper is only one example. There are a few other options as well. Zoom transcript, for example, is a pretty good option for multilingual speech. That's something that you can also try.
Thank you. I was also wondering if there are any database where I can get some transcript for training. Are they like?
I think Hugging Face would be your best bet. So let me just do a quick search. I haven't searched for I think. So if you, it does allow you to search and it will try to give you all of the data sets that it has available. So over here, it has a young children's speech data in Mandarin, and it has a, if you look at the model card, this will tell you how much data each of that has, and I can add the link to my search results over here.
Yeah.
So usually if people have open data sets, they try to create a model card on and allow people to access it through Hugging Face. So this is something that you can use.
Yeah, I also foresee, so for example, images, we have like image augmentation. So for voices, I foresee my input voice to be very agitated, like not as stable as the sample voice. So do you recommend any like augmentation or processing method?
So when you say agitated, do you mean there's going to be a lot of background noise, or do you mean that the emotional state of the speaker is going to be?
Yeah, the emotional state where the pitch may be like much higher and faster frequency.
It's possible that if you use a voice like if your input clone voice is very agitated, it's possible that your output voice might also share the same emotional state. I have actually not tested this, and I think it's a really interesting example that you've brought up. I would recommend just testing it with this. 1 second. So the test usually just takes a couple of minutes. So if you have a few minutes, you can just try it out by changing the sample voice and see how it works. You can simply upload like a sample. You can call it give the audio file anything and see how it does. But thank you for that question. I'm very curious to see if you give an agitated voice for the cloning technology, does it give you an output which is also agitated, or does it?
Yeah, thank you so much. Thank you.
Yeah. Do email me if you're like with your results and tell me how it went.